Okay, so thanks very much, everyone. The next speaker is Ralf Jung, who will be telling us about using formal methods to keep unsafe Rust in check.
Yes, thanks a lot for the introduction. And as you can see, I spontaneously changed the title of this, but too late to get it into print, because the talk developed a bit while I was preparing the slides. So yeah, this is about Rust and formal methods, which I think is a great match. I'm going to try to convince you of that. But before I get started, maybe a few words about myself. I'm an assistant professor at ETH Zurich for 2 years now, and already during my PhD, I have worked heavily on the Rust language from the academic side, and we'll hear a brief glimpse of that also during this talk. But I'm not just involved in Rust academically, I'm also involved directly in the Rust project as an active contributor to the project since 2017, with at this point multiple thousand pull requests. I'm one of the co-leads of the Rust operational semantics teams, so if Rust has something like a chief specificationist or whatever the job title was we were talking about yesterday, then I'm one of them. And I'm advisor to the Rust language team, which is the team making the final decisions about new things being added to the Rust language proper. So I've done a whole bunch of Rust stuff, basically. But let's get started with the talk. So we all heard many times Rust is a memory-safe language. Maybe we don't know what memory-safe means, but we got the White House seal of approval on statements like that, so it can't be wrong. But what exactly does that even mean? So let's look at a concrete example of the kind of issues Rust would prevent. Here's a little program. It starts by creating a vector, which is the Rust name for a heap-allocated growable array. And initially we put 0 and 1 in there. So somewhere in memory on the heap, we have a buffer with these two numbers, and v is a pointer to that buffer. Then we create p as a reference to the first element of the buffer, because that's something Rust supports. You can get references to in-place data, which is more efficient than having pointer interactions everywhere, like you would in most managed languages. Then we call push on the vector, and so now something very interesting happens. In our hypothetical scenario here, there's not enough space in the existing vector to store the additional element 2, so we have to reserve a larger chunk of space somewhere else in memory, copy everything else over, add the 2 at the end, and then we deallocate the old buffer because it's no longer needed, right? We've moved everything somewhere else. This is now stale data that we don't want to have lying around. But of course now we have a problem, as you can see on the image, because our reference p still points to the old buffer. If you try to write to that, we have a problem. This is a use after free write. This could easily turn into a security issue if this overwrites the wrong kind of data. So lucky enough, none of this actually happens, because if we try to compile code like that, the Rust compiler stops us. This is the sense in which the Rust compiler guarantees memory safety. And now, while that might look like a very contrived example, situations like this can easily arrive in real-world code. So here's some hypothetical C++ code working on a vector that is just got as a reference from somewhere, and it is iterating over the vector, and an iterator is basically a pointer. So you can think of this it here as being the same thing as the p in our previous example. And somewhere inside this loop, we call a function, and because there might be aliasing everywhere, it's very possible that this function actually has access to the same vector via something, and pushes to it. And then we have exactly the same situation as what we did before, where we are invalidating a buffer while we have an iterator running over it. This is in fact a problem that's common enough to have a name. It's called iterator invalidation, and it doesn't just plague languages like C++, it plagues even safe languages like Java, where of course it doesn't cause arbitrary crashes, but it can still cause exceptions or logic bugs. So it's still an actual problem, which Rust fundamentally prevents via its safety mechanisms. So how does Rust do this? Well, the key kind of insight of the designers of Rust is that this is the problematic shape that we have to prevent. We have two pointers or references to the same data. This situation is called aliasing. And now we are using one of those to perform a mutation, or in this concrete example, a deallocation of the relevant memory. And from the perspective of the other pointer, p, this is kind of a spooky action at a distance, right? We didn't do anything with p, but suddenly p goes away. This is super hard to reason about for humans. This is super hard to reason about for tools. There's been hundreds of papers, probably thousands of papers about that. This is kind of, from the Rust perspective, the root of all evil. So the answer that they had is, don't do this. The Rust type system is all about systematically preventing alias mutable state. And so corresponding to that, Rust has two reference types. One, which is the so-called mutable reference, which, as you might guess from the name, is indeed mutable, but hence rejects aliasing. And the other one called a shared reference, which allows aliasing, sharing, but rejects mutation. Now this may seem like it's completely impossible to program in a language like this, because if you look at most programs written in other languages, they have shared mutable state everywhere. But to some extent, that's just because this is easy in those languages, maybe too easy, and it is how we teach our students to program. So everything is just alias everywhere. In many cases, you can restructure your code to avoid that. And then you can write it entirely in this discipline of Rust without losing expressivity. However, of course, sometimes you actually do need shared mutable state. And so the Rust answer to that is that Rust is really two languages. On the one hand, we have safe Rust, which is a very happy place where everything is nice, and where we have guaranteed memory safety and thread safety. This is kind of the by-construction part that was mentioned in an earlier talk today. And this is maybe around 95% of the language. It's a bit hard to put a concrete number on that, so don't quote me on this, but this is the rough ballpark that it seems to be around. And then we have the remaining 5% of the language, which is unsafe Rust, which is what you do when you do things which are kind of too clever for the compiler to understand why what you're doing makes any sense. So in unsafe Rust, you have full control, you get to do all your low-level C tricks, but also it's a dangerous place to be in. There are monsters lurking in the depth of unsafe Rust. The monster is called undefined behavior, and we will hear more about it in a bit. So for the rest of the talk, I will first be talking about how safe Rust is actually not just nice for being safe, but actually also nice for reasoning about. And then I will be talking about unsafe Rust. But let's get started with the safe part. So here I have the signature of a Rust function, not quite how I would actually write it, but for demonstration purposes, which sorts an array in place, or rather a vector. So this is a mutable reference to a vector of integers, which the function is supposed to sort just where they are. So this can be very efficient, kind of quicksort style implementation that avoids having unnecessary extra allocations, can be very fast. But if we think logically about what the function does, we know that this mutable reference isn't aliased with anything else. So as far as we are concerned, when we are trying to think about or describe the input-output behavior of this function, this is really kind of the same as a function that takes a list and returns a different list. It's just it's returned in the same place where we found the old list. But logically, those are entirely the same things. If we had written this in a pure programming language, we would have written the one below. It would have been a bit less efficient because we can't do the nice in-place updates. But in terms of what we have to say about specifying this function, in terms of pre-post conditions or anything like that, it would be exactly the same thing. So this is despite the fact that this function is very imperative, but it has a side effect. It mutates memory in place. But logically speaking, entirely safe Rust code is basically pure code. And so this is the key insight of a work that was published at this point, I'm not even quite sure, 5 or 6 years ago, Rust-Torn by Yusuke Matsushita from Tokyo, where he realized that if we have a shared reference, it's characterized entirely by its value. So this shouldn't be too surprising because shared references can't change. So the reference identity doesn't really matter. It's only about what the reference points to. And we are merely just more efficiently passing this value around. By passing it by reference, we're not changing the nature of what we are logically doing. And there is an asterisk here for an exception I will get back to later. And then mutable references are completely characterized by the value they have right now and the value they will have at the end of their lifetime when they can no longer be used. This is not at all obvious. And proving this was a big feat. So I have the references for that at the bottom, and I would assume, like Matthew, that these slides will appear somewhere where you can click the links. But working on this, building on this, we can now do verification with this insight. So we can use, in particular, basic first-order reasoning to reason about heap manipulating program. We no longer have to worry about aliasing. We don't have to use separation logic. We can verify these programs as if we are verifying Haskell programs. And at least common wisdom has it that it's easier to verify Haskell than it is to verify C. So one of the, or maybe the most most developed Rust verification tool is Creusot by Xavier Denis and others in Paris, which is entirely based on this insight and is kind of one of the main case studies to show that this actually works in practice and that gives a very good verification experience. There's a set server called Creusat, which is using modern set solving techniques, which is on par in terms of performance with other verified set servers, but was developed in a fraction of the time. In particular, this was developed as a master thesis by someone who hadn't really done much verification before. So in half a year, they wrote the thing and verified it. It's about 1,000 lines of code with 3,000 lines of proofs and spec. So I think there's further improvements to be done here, but it's not a terrible proof to code ratio for like some very non-trivial correctness properties. But of course, we can also take this insight that Rust is basically pure, a bit more literal, and this is in fact something that was already mentioned earlier today, and have a tool that literally just translates Rust into a pure language based on exactly that insight, which is what NAS is doing, and they have a whole bunch of backends where you can now continue your reasoning by relating your Rust code to your existing theories. Like you have crypto code, you translate it into F star, and now you can connect it to all the things you've proven in F star about various crypto primitives. So in safe Rust, things are very nice in terms of verification. Much nicer than you would expect from an imperative efficient language. Now, what about unsafe Rust? Well, whoops, I am sorry for that. I will have to did some slide editing, and it seems I accidentally cut out the second half of my talk. So while the slides are rebuilding, so as I already mentioned, the point of unsafe Rust is that it is why is this all black now? Is that we use it whenever we are now overloading my PDF reader here apparently. Is that we are using it whenever we are writing code which is correct but too subtle for the compiler to understand. Because of course in general that's an undecidable problem. So we've already seen the vec type earlier. As an example of that, this is a growable array doing kind of as much as possible, staying in place on the heap, managing that a part of this buffer is uninitialized. This is tricky code to get right. It's too tricky for the Rust compiler to understand. It's crucial for efficiency. We use unsafe code internally in that. Rust also has this archetype, which is an atomic or thread-safe reference counting pointer. And again, making sure that we get the reference counting and the atomic primitives right is not something the compiler can check. And mutex is a very interesting type here, because mutex is Rust's way of providing a lock to users, which is shared mutable state, even in a concurrent program, kind of directly exposed to Rust programmers. So it's great that we have these tools available, but of course this is a great power which comes with great responsibility. It's very dangerous, it's a sharp knife, it's very dangerous to write unsafe Rust code, because there is this monster lurking there, where if you're not careful, then your code has undefined behavior, which I could spend an entire talk just talking about that, but the loose definition is that it is a violation of a compiler assumed requirement. And this in particular includes all memory safety violations. Compiler assumes you're not doing out of bounds and things like that. So you might think now, well, is this really so bad, this monster? Yes, it is. So I've brought a simple example demonstrating the kind of things that can happen when your code has undefined behavior. One of the things that is undefined behavior is doing the wrong thing with uninitialized memory. So here's an example program which creates some uninitialized memory and turns it into an integer, which is blatantly wrong. You should never do this, but we can just see what happens if we do it anyway. Right? Let's break the rule and see what breaks. So the next thing the program does is check a trivial tautology, ensuring that the integer we got is less than, equal to, or greater than 0, which obviously should always be true. But if we compile this code on the current stable Rust compiler with optimizations enabled, we get that the assertion fails. So somehow Rust found a new integer. I guess we should call our mathematician friends and tell them about this discovery, because we now know that there is some integer which is neither less than or equal to nor greater than 0, so that's amazing. And even better, if we try to ask Rust what is that integer by printing the number before the assertion just, the bug goes away. Like when we look at it closer, behavior changes. So this is a complete nightmare. We have code with undefined behavior, and the consequence of this is complete logic and nonsense. It is Heisenberg's where debugging the code leads to changing behavior in the code, so it's basically undebuggable. And of course, it leads to security vulnerabilities, because all cases of out-of-bounds reads or writes, use after freeze, all of these things in Rust are undefined, are instances of undefined behavior, and therefore kind of also included in this. So as we've already heard, we can still cite this number. Around 2/3 of the security vulnerabilities are caused by memory safety, which means about 2/3 of security vulnerabilities are caused by undefined behavior. So UB is a big problem, and it may now seem, given that unsafe Rust has this risk of having UB, the presence of unsafe Rust completely undermines Rust's safety story. But that is not the case, because the way we use unsafe code in Rust is we carefully isolate it. So we have unsafe code inside VEC, but then the public API we provide for VEC is carefully designed so that if you're just using it from the outside, then the library author guarantees to you that you don't have to worry about undefined behavior. The iterator exposed by VEC ensures that you're not pushing to it while iterating, and it uses the rich type system of Rust to provide these assurances. And this is particularly interesting for mutex, which provides shared mutable state, but it does so carefully in a way that the Rust type system guarantees that while you're accessing the data gathered by the mutex, you always hold your lock. You cannot forget to do this to acquire the lock, and once you release the lock, you can no longer access the data. So we can actually safely expose shared mutable state to the Rust programmer without the compiler even realizing that shared mutable state is a thing. The compiler is just enforcing the types of all of the functions on the mutex API boundary. So one of the core results of my PhD as part of this Rust-Belt project was to formally prove this claim, at least on a somewhat idealistic model of Rust, that if the unsafe libraries are what we call sound, so basically well encapsulated, then the entire program is indeed safe. So memory safety isn't just for completely well-tiled programs, it is also for programs that contain unsafe code in this carefully managed way. So this is great news because it means we can now start to tackle this problem of UB locally, right? All UB has to be kind of guarded within this little bubble of where it is defined and then exposed to safe code. So we can focus our efforts on locally ensuring that indeed there is no UB in those places. But it is still a hard question to answer whether a given code has UB. I mean, I've showed you an example earlier where if we run the code with optimizations, it does some logic and nonsense, but if we change the code slightly, it stops having logic and nonsense. So it's really, really hard to test for UB. Your code might have UB, but work fine for years because the UB was just latent and the code patterns never quite aligned to make the optimizer do the weird thing. But then you change your code somewhere else, or you change a dependency that gets inlined into you, or you update your compiler, and suddenly the UB surfaces. It's really hard to be sure that you don't have UB in your code. So this is where a tool that I'm working on comes in. MIRI is an undefined behavior detection and testing tool for Rust, because just telling developers that they have to be careful and avoid UB doesn't work in practice. We've seen this in other languages that have similar problems. So the key thing that MIRI does is it is, again, a testing tool, and it runs the code like an interpreter, line for line, where it keeps track of the machine state in a heavily instrumented way. So we don't just have memory somewhere, we know exactly which memory is allocated where, we know which part of it is initialized, we know all sorts of extra metadata, so that we can check all of the undefined behavior. And with that, there's tons of cases of undefined behavior that MIRI detects. And indeed, my claim is it detects all of the undefined behavior that can affect the correctness of a Rust program. So that's great. That's something that unsafe code authors can and do use in practice. So MIRI has found plenty of real-world bugs. Here's an excerpt of the list there, but the list is far from complete because at this point MIRI has become a standard tool that is used on continuous integration, even for the Rust standard library itself. So at this point MIRI is preventing these bugs before they even hit the code base, which also means we no longer get told about them to add them to the list. So if you have a good test suite, this can give you some base insurance that your code indeed doesn't have undefined behavior. But of course it's still testing. What you really want is some sort of verification or some sort of more exhaustive testing. So what are the possibilities in that space? Well, one of the things you can do is you can go from just testing to a form of model checking. So this is the Kani tool that we also heard about yesterday during the lightning talks by the people at AWS, which is able to check for UB. It has some model of unsafe Rust. It's less close to like the real actual compiler spec, which is a hypothetical spec than MIRI, but it runs as a model checker. It can cover many more executions at the same time. And of course, we can also go to full deductive verification, giving unbounded correctness guarantees, and there's a number of tools that are being developed in that space on various trade-offs between how much they are like foundational tools proven correct in Coq versus relying on SMT servers versus how things are specified exactly. And some of these tools are even able to not just verify that a particular function is UB-free under certain preconditions, but to even verify soundness which is a key result because it means that even unverified clients benefit from this. Like generally, if you do verification, you state some preconditions, and that kind of means only a verified client benefits from this because you have to ensure someone has to ensure that these preconditions are satisfied. If you prove soundness, then you are proving that all safe code is UB-free, even if you haven't verified the safe code using the library. And one of the amazing things about soundness is that nobody needs to write a specification for it because the author of the library already wrote a spec by decorating all of the functions with the right types. So in a sense, in principle, it's a completely well-defined question to just take a random Rust library from out there, which has unsafe code inside of it, and just ask, is this sound, yes or no? And you could imagine a tool, so of course horrendously undecidable, that is able to answer this question. So I'm hopeful, I'm curious what will happen as people start to explore more and more going into fully automated ways of attacking this. So this is the part of my talk where I have the obligatory mention of AI tools maybe coming up with the right invariants, which can then be checked by other tools to ensure that they indeed cover the complete API and having some sort of feedback cycle until the right invariant is formed. Or really, you can knock yourself out and try absolutely anything. And there's an infinite supply, or basically infinite supply of case studies out there in the Rust ecosystem that you can try the tool on. So I think this is a great way to have kind of not need specifications and have a great supply of challenging verification problems. But of course, if you want to actually verify something, we would also need a spec for the language itself. If we want to really exclude UB, we need to know kind of authoritatively what is the UB of the Rust language. And famously, Rust doesn't have a specification yet. And I would like Rust to be on this illustrious list that Peter yesterday had in his talk about all these nice interfaces that have formal specifications. So another project of mine that I'm working on is mini Rust, where I want to develop exactly that. So this is a work in progress, formally specified core language for Rust. Core language meaning it's expressive enough to cover everything Rust does with as few primitives as possible to cover that space. And the key idea behind mini Rust is that we can take what we learned from Miri and translate that into the specification. Because the error mode we want to prevent is having a spec which is disconnected from reality, having a spec which declares all sorts of code UB, even though these are things programmers do and have to do to get their work done. But because Miri is a tool that is already used out there, if code is accepted by Miri, if UB is rejected by Miri, then at least there's a lot of code out there which successfully runs without that kind of UB. It's a realistic specification. And so we can use that to inform the authoritative specification that we write. And ideally, Miri would be an exact one-to-one implementation of that specification. So the goal is for mini Rust to become the official source of truth, kind of normatively decided upon by the Rust community, similar to what we just heard about for WebAssembly for undefined behavior in Rust. It will be machine readable. We can prove theorems about it and with it using Coq. And it will be grounded in reality by matching what Miri does. And the team that is in charge of writing the Rust specification has already said that in general they are on board with this approach. Mini Rust seems like a great way to specify the operational semantics aspect of Rust. So here, as a brief summary slide, is an overview of all of the Rust verification tools. Well, probably not all of them. There's too many, and I haven't mentioned all of them, even those for time reasons. But you can see that there's broadly a divide among tools that only work on safe code, and safe code here excludes things like mutex, which is shared mutable state, right? So this is only the fragment of safe code which doesn't need interior mutability, which really behaves like a pure program, and then tools which do run on safe code. And in the middle you have Miri and Kali, which are kind of a bit special because they don't do full-blown verification, but they also don't require annotations, and you can just run them kind of on any code. So yeah, with that I would like to conclude. I think Rust is a great target for formal methods. There's a lot of momentum. We've seen there's tons of tools. I'm very excited to see what happens as this community keeps developing and growing these verification tools. I think there's a great future ahead for Rust being also a great choice for verifying all of your code. Because most of the safe code can be treated as pure, so the problem becomes a lot simpler than it would in most other languages. And for unsafe code, there's a generally accepted local correctness requirement where we have to ensure our programs are sound and do not cause undefined behavior, which is already a social consensus among the Rust community that that's how we want to write our code. We just need the tools to help them ensure that this is indeed the case. So thanks for your attention.